Collaborative Robotics Training Days. My name is Steve Crow. I'm the executive editor of robotics at WTWH Media. I'll be your moderator today. Really appreciate everybody being here. This is our first session in Collaborative Robotics Training Days, and we'll be discussing today collaborative robots and intelligent motion control. Today's presentation will focus on servo actuators that function as end effectors, often mounted on transport systems such as robotic arms. These devices include linear actuators, force feedback actuators, voice coils, and much more. Understanding their capabilities and their properties will help ensure that your next application delivers exactly what it is that you're looking for. We'll also be covering the role of ultra-precise motion control and miniaturization. You'll learn about new technology offerings, including an ultra-compact PCB-mountable high-performance motion controller that's really gaining some popularity amongst robotics engineers. Before we get to our speaker today, we do have to go over a couple of house cleaning items. We get this question probably the most. The talk will be available on demand shortly after it ends. You'll be able to re-listen to it at roboweeks.com. If you're just re-listening to it, use the same login information that you used today to access this talk on demand. Of course, you can always share it with your colleagues as well, but they'll have to register on their own. Hopefully you see a couple of different boxes on your screen. You should see a Q&A box and a resources box. We'll be having a Q&A with today's presenter at the end of the talk. So please enter any questions that come to mind into that Q&A box. If time does not allow us to answer all of those, we'll make sure that we pass them along to Prab after the talk ends. Just a note, if you're listening to this on demand, if you weren't able to join us live and you're catching this late, you can still ask questions. We'll receive them in our back-end dashboard. And again, we'll forward them onto Prab as they come in. You should also see a resources box on your screen. The slides from today's presentation should be available in that resources box. And there's also an additional white paper in there from Performance Motion Devices in case you're interested in learning a little bit more about what they'll be sharing today during today's talk. So again, this is our first talk in our Collaborative Robotics Training Day series. This series, as you can see on the agenda on your screen, it runs once a week for about a month, and it's designed to provide a snapshot of the current state of collaborative robotics, which is one of the fastest growing market segments within industrial robotics. So we'll be covering new capabilities, powerful enabling technologies, which is what we're doing today. We'll share real-world case studies about emerging and established cobot applications. You'll hear from some of the best minds in the market. We'll also be talking to you about how to select, how to program, deploy, and manage collaborative robotics work cells. Again, you can see the agenda on your screen, and if you haven't registered for these upcoming sessions, you can also do that at roboweeks.com. A little bit later on in the year, we'll also have a couple additional series as well. Same format, running once a week for about a month. We'll be running robotics engineering training days from May 24th to June 28th. That'll be about enabling technologies that will help robotics developers throughout their commercial robotics development journey. And then September 13th to October 11th, we'll be running mobile robotics training days, which will provide a snapshot of the mobile robotics industry, so AMRs. What are some powerful enabling technologies for AMRs? What are some established and emerging applications for AMRs as well? And you can find out all the details and register for those events as well. There's not a lot of information up about those events yet. There will be in the coming weeks. But again, you can find all that information at roboweeks.com. I do want to thank today's presenters. Wouldn't be possible without all of their support. Again, our presenting sponsor for this specific session is Performance Motion Devices. This is also brought to you by Chief Tech Precision and Wago. So again, thank you to without their support, this event and future events that we put on would not be possible without their support. With that, I'm going to introduce today's speaker. I'm sure a lot of folks have heard from Prab. He's spoken for us a number of times online and at our in-person events. So it's Prab Gaurasankaran. He's the VP of Engineering and Strategy at Performance Motion Devices. He has more than 20 years of experience in technology, in product management, hardware development, and engineering leadership. You'll also be able to catch Prab in person at our upcoming Healthcare Robotics Engineering Forum and Robotics Summit event that takes place May 10th and 11th in Boston. He's tremendously knowledgeable about all of this stuff, and we really appreciate Prab taking the time out of his day to join us today. So without further ado, Prab, the floor is yours, sir. Take it away. Thank you.
Thanks a lot, Steve. So I just wanted to try to, this will be more of a tech talk, kind of try to give a little bit of background in terms of different technologies that are used in end effectors and collaborative robots. So I just wanted to try to touch on a few key things. So we'll look at linear actuators. There are actually a lot of different types of linear actuators. We'll also look at force control. What are the key concepts? Using a sensor versus sensorless, and how do you do control of them? On the linear actuator side, we'll actually kind of look at servo-controlled actuators. It could be DC brush or brushless DC. Then we'll try to focus on key control techniques for controlling these actuators. And then we'll try to dive in a little bit on the control algorithms that are used to control these actuators and how to actually get force feedback. If time permits, we'll look at a few more robotic motion design challenges. And then I typically like to conclude with just a presentation of a few of our newer products and then an application example just to show you visually what it looks like in your product. So with that, let me just give you a quick background of who we are. So Performance Motion Device has been around for 30 years. So we control over 6.5 million motors worldwide. So we're used in lots of different end markets, from robotics to mobile robotics to lab automation, semiconductor. So anywhere where there's motion, where you have to move a motor precisely, PMD is involved. And we do a broad range of products. So we do digital drives, which are pretty popular in the mobile robotic space. And then you can go up and down the chain. So if you have higher volume, you can go up to integrated circuits and design your own board. We also do digital amplifiers. And then for smaller volume, quick turn stuff, we also do motion control boards. And the key to keeping it all working together is the C-Motion SDK that we provide that works across our products. So you can start with a digital drive and then migrate to an IC or go to a board. With that, let's just get started, and then we'll kind of look at a quick intro on linear actuators. There are quite a few. So motors and other types of electric actuators come in lots of different shapes. But compared to actuators that transport an object from point A to point B and focus on position control, the end effectors that you kind of see a picture of in this one has to do some sort of force sensing, right? To make sure the object that's being carried are not crushed or dropped. And so force sensing function, it may not require separate hardware. So just the controller that you use to control the linear actuator or motor can be used in sophisticated motor control techniques. So we'll take a look at that. So especially in the cobot case, there's a lot of force control and force feedback that you have to apply. And you can implement a lot of these in terms of algorithms for force control. So just to dive a little bit deeper into linear actuators. So there are two different types. So you can actually get, so if you look at end effectors, you typically are linear servo actuators. So there are a few different varieties, but the most common configuration is a rotary motor that's used to create linear motion. So the rotary motor is often used, a DC brush or a brushless DC motor, although step motors can be used. So as the motor rotates, a mechanism such as a lead screw converts the rotary motion into linear motion. They come in lots of different sizes, strokes, and force output. So these actuators are kind of characterized by high force output, moderate speed, and moderate positioning accuracy. So the range of applications of this type of actuator is vast. It includes electronic manufacturing. So you look at pick and place kind of machines, semiconductor equipment, biotech. You see it a lot in robotics and industrial automation. So just diving into one, so we'll just kind of walk through a few different types that we have seen as part of controlling these motors. So a secondary category of these linear servo actuators is these direct drive brushless DC motors. So they are like a normal rotary brushless motor, but these are commutated servo controlled motors, which typically use an encoder for position control. So the direct drive here means the linear motion is directly generated by the motor coils and magnets. There's no lead screw or gears or pulleys that are needed to convert a rotary to linear motion. So the linear version of a brushless DC motor is essentially an unwrapped version of a rotary motor. So this is just diving in a little bit deeper into what the insides of a motor look like. On the left, you see the rotary motor, and then you see the flattened linear motor. So they both have a stator, the part that houses the coils, and then they both have a rotor, the part that contains the permanent magnet. So the rotor is the permanent magnet, and the stator is the coils. So as we shall see, using the term rotor is confusing for a linear motor, but since it doesn't rotate, but we'll just kind of walk through and use that as our terminology. So just looking at a few different configurations of linear actuators. So there's typically, we see two different configurations that are possible for both the stator and rotor. So the stator, which is part of the coil, is stationary, and the rotor, which is the moving part, is where the magnets are. So as you can see in the first one, the coil, which is the stator, is stationary, and the rotor, which is the part with the magnet, moves in the first picture on the left. And in the second one, you see where the stator moves, which is the coils move and the magnets are stationary. So the choice of configuration between the two comes down to cost and mechanical considerations, right? Is depending on how long your stroke is and how big your XY table is. It tends to lean itself to one of these choices. The longer stroke devices often reverses with what happens is the smaller stator assembly moving along a relatively long track. So if you look at a longer stroke device, it's usually the configuration on the right, and the shorter stroke devices are the configuration on the left. But both are controlled similarly. So you get a similar servo brushless kind of control. So there's one more direct drive configuration that we have seen, which is a rod-shaped rotor as opposed to a track that you saw in the previous slide. The rod contains the magnets, and as before, either the rod can move with the stator being stationary, which is the coils, or the stator can move along the line. So whichever arrangement you use, the brushless DC motor is the workhorse for the application to provide like high precision, highly reliable, quick response time. So compared to rotary ones, the linear actuators, direct drive motors, have very high acceleration and moderate torque output. Although direct drive motors are expensive, you still find them in lots of different industries, especially where you want high precision motion. So this another category of direct drive linear actuators is these linear DC motors. So it has two flavors, a moving magnetic rod arrangement and a voice coil arrangement. Actually, the voice coil is something a lot of people are familiar with. The magnetic rod style DC linear actuator can deliver modest torque and speeds with a small to modest stroke distance. Its main advantage is its lower cost and it's simpler. The voice coil actuator reverses the role of the stator in the rod magnets. The actuator has a shorter stroke, modest torque output, but extremely fast response time. The speed is due to the fact that the moving portion can be very light, consisting of little more than coils themselves held together by adhesives. So you can see the voice coil motor on the right, and it's a lot of people have heard of voice coil motors because actually a ton of audio equipment and stereo equipment use voice coil motors in them. So just now that we have a background on few different types of linear actuators, the direct drive motors, um, we want to try to kind of jump into how do you control force, right? What are the force control key concepts? Um, so if you look at the applications where force control is key, is like gripper kind of applications in the cobot space. You have the screw cap application, the press fit machinery, packaging. So there's a lot of different use cases where the force control is critical. So the first part of the move kind of engages the object, where you kind of go try to squeeze the object. And the second part of the move establishes the actual squeeze force. So we'll, as we go along with the slides, we'll kind of show you how you can achieve this control, both with and without sensors. So as you see here, so you're looking at two different techniques. So first one we'll talk about, we call it the position determines the force grip method. In this approach, the actuator is controlled by like a servo PID loop, which is in our motor controller. So the PID stands for proportional integral derivative. So it continuously monitors the motor torque output command. At the start, the gripper is not in contact with the object to be gripped and begins a trajectory move, as you see in the position graph in the bottom. As the move proceeds, at some point, the gripper makes contact with the object. This results in the servo loop increasing the commanded torque as it attempts to follow the trajectory. So when the torque equals the desired grip force, the trajectory is halted. So as you see in the graph on the right, so you have the position, the grip move begins, and as you engage with the object, the grip force, you stop, the threshold is reached, and then the trajectory is halted. So the gripping move is not complete, and the arm can move with the gripped object held in place. So since the position of the actuator is fixed, the actual applied grip force may vary depending on the compliance of your gripped object. So this is the position determining force grip method. So the other one that we've seen is where you actually apply a very specific force limit. So in this second approach, we call it the set explicit force limit method. The gripper similarly approaches the object using a commanded trajectory move, but the servo loop does not monitor the force output or halt the trajectory when a threshold is reached. Instead, so you use the current output limit is programmed into the servo loop, so that even if the PID tries to follow the trajectory, the force it can apply is limited. It stops. The force applied is limited based on the current, and then you can continue traversing. So as you see, the trajectory doesn't end. You can continue through your path. So if the object being gripped compliantly deforms or presents a different force during the acceleration, the actuator position will move forward or backward in such a way that it applies the threshold grip force. So these are two common techniques that we've seen for force control. And what we've typically seen, in some cases, you can actually implement sensors, torque sensor or strain gauges and stuff. But we've seen plenty of applications where it's just an algorithmic magic, we call it, that's applied to detect the force as part of the servo control loop. So as you see, what is shown is a common PID loop. So you can implement both of these grip strategies as long as it has the ability to compare the output torque command with a threshold and support a programmable torque limit. In the control algorithm that's shown here, there are two separate control loops. There's a position loop and a current loop on the inside. The current loops are also called torque loops, depending on which controller you use. So a separate current loop is critical because the accurate force control is come back, as you see in the slide, you need a clear measurement of the actual current because that controls the torque applied or the force that's applied. So as mentioned earlier, the key assumption of actual force control if you don't have an external sensor, is that there's only a small amount of friction between the direct drive actuator and the object that's being controlled. So we can actually, so what the coil current that you're getting back is a clear indication of the force. Um, but what you see is even with geared motors can sense force if the gear ratio is modest and the gearbox is low friction. So these are kind of applicable for cobots that have direct drive motors that excel at meeting this requirement because there's not a lot of friction. The current actually equates to the force applied, and you can use this algorithm as it's shown to kind of control that and get the force effect in there. The other methodology we see is where a torque sensor is used. So in this particular case, it's typically common where you have like a reed screw rotary to linear actuation or some other, there's a mechanical structure to it, there's belts and stuff, so where it's hard to measure, where the current doesn't directly respond to the force applied. So in this case, the outer loop is a commanded force. So in the top, it shows an N series, it's a newer drive. So we have a separate analog input in the drive where you could take the linear actuator strain gauge measurement and you use it to run an outer loop. So you kind of run a cascaded force and a velocity control loop in there. And in this case, the grip force is explicitly controlled. This is the second one where the grip force is controlled, and then you can continue to traverse in your trajectory. And here a strain gauge is used, and it's kind of populated in through an analog input to the drive. So the commanded force is compared with the actual force measurement from the strain gauge, and then the PID loop is controlling the force error. And then we'll talk about the deadband filter, and then you control the velocity as a second stage. So as we talked about, there's also a bandpass filter in the middle. In a lot of these cascaded force velocity loops, what you see is you need a filter in the middle because it's called a deadband filter. It's usually put in there to kind of reduce hunting. So when the needed velocity command is close to zero, it's not truly zero, but it's kind of close to it. You can set a threshold, and then this deadband bandpass filter will kind of allow you to result in quieter operation, right? So where you're not hunting for the exact zero, where the precision is not needed, you want to be close enough to zero, a certain threshold. And this helps actually improve the loop stability. So it's not constantly trying to get to zero. And then it reduces noise and saves energy. So just to summarize, we kind of walked through the different types of linear actuators. I know there's a lot of details here, but all the slides are available offline. So you can kind of look at the different types of linear actuators that are available, right, for your design. So depending on whether you want high torque output or accuracy or speed acceleration, you can kind of choose the type of linear actuator and the linear drive you use. And then again, you have a few different ways of controlling it. You could do position determines force methodology or the torque limit determines force. And you could use an external strain gauge or a torque sensor back onto an analog input. So there's a few different ways to control the force. So obviously at PMD, we work closely with our customers to kind of help them try to understand which algorithm works better, what are the pluses and minuses. And in some case, adding an external sensor is, because it's implemented in a small space, it's a lot of extra work. So we could do it with the control loops and kind of setting the parameters correctly. So that was a quick view on the linear actuators and the force control techniques that we have, both with sensors and without sensors. We can now jump into a few other robotic design challenges that we've seen with a lot of our customers, right? The first one is the non-Cartesian motion, where it's not a clean XY motion. How do you solve it? Where does the math for the kinematics happen? The second design challenge is the dynamic load management, where if you have variability in load, how do you accurately control position? And then we'll look at a few other design challenges. So the first one is the non-Cartesian motion management, which has the path planning and the inverse kinematics. In this, just to give you a background, I'm sure most of you are familiar with it. So if you look at a simple example of a Cartesian motion is an XY table, right? If you take a gantry with XYZ, that's a typical example of Cartesian motion. So where you have a motor per axis, and it's kind of doing, you have to give it positions in both X and Y directions. So to get to this curve, you have to give it X position and Y position, and you get this motion. You can achieve this motion. So this is very common with gantries. So the non-Cartesian motion is the most common in terms of collaborative robots or scalar robots, especially with an arm. So this four axes of motion is very common in a scalar robot. So the shoulder and the elbow motion contributes to the destination of the endpoint, XY. So as this slide kind of shows, right, it's the X position is a combination of the shoulder joint, the elbow, and the wrist, and then there's a bunch of math that's done to calculate the exact XY position. So this is typically this inverse kinematics. We'll talk about it later, where you can, in a centralized control setting, there's like you take a bigger ABB or KUKA robot, there's a central controller that's doing all this inverse kinematics and computing exact position and angles and sending it out to each of the joints. But for smaller systems, you can actually do some of these inverse kinematics in the controller. And we'll look at a few techniques to try to do that. The other problem we talked about is the linkages. So if you look at non-Cartesian motion, right, the motion is not perfectly linear in the sense you have joints that might bind at certain points in the motion. And so your actual trajectory, if you look at the velocity, they are not perfectly linear. They go through. So how do you kind of get clean, smooth motion from a mechanical construction that's not perfect? So we'll look at a few techniques to solve that problem. So compute of inverse kinematics, obviously you can do it. This just shows a list of equations that you have to solve. So you can do them in software. Obviously, you need a lot of compute power. So in the smaller embedded drives, you can still do them, but not at the speeds that you want them to. So obviously, you want to try to come up with a way to avoid this math calculation. So there's a few different approaches. So one is we kind of look at these, break the profile into pieces, or segmented profile approach. So you say you take a complex shape, you can actually break them down into individual profiles, and then you can have these breakpoints that say, oh, where are you now? And then you can implement them with breakpoints. That's one approach. The most common approach is this translation lookup table. So it's essentially you're taking all the different angles. So instead of having to do the inverse kinematics, you're looking up a lookup table. So what it is makes an effective inverse kinematics for X number of points. So depending on the number of points that you're traversing, the tables could get bigger. But a lot of the embedded drives still have a lot of memory capacity. So you can load up a full two-dimensional translation table in them. And that way they can just do a quick lookup without having to do the math. And this is very common in a lot of the mobile robotics kind of applications. So that was a quick view on how to solve some of this inverse kinematics. So you can try to do it through a translation lookup table, trying to avoid having to do the math in your software. The other part we see a lot is this dynamic load management. There's a couple of solutions with intelligent feed forward and compliance compensation. So what happens is typically you would try to fine tune your motors and the loops, right, for clean, precise motion. But even despite trying to do all the PID tuning of all the parameters, you cannot perfectly track the profile because there's either a lag during acceleration or there's an overshoot during deceleration, as the pictures show on the right. So it tends to lead to inaccurate positioning. So compliance, again, is a broad term, but if you have mechanical linkages or gears or bells, they're not infinitely stiff. So you have, if you do the map, you'll have a zone. So you'd have to do a little bit of dynamic compensation during the robot motion to have precise motion. So what we've seen used, what we do a lot of is this feed forward to improve your position accuracy. So you can actually introduce a feed forward table to your PID loop, and you can actually, in the lab, as in manufacturing, you can actually calibrate these. So as based on the mechanical construction of your machine, you can figure out the torque deflection table, and there's some techniques to figure them out. And then in terms of the controls, you apply them as a feed forward into your PID. So you add it in as you're computing a position error. And this kind of helps you get much better position accuracy as you're trying to move through. So that was a very quick overview. Obviously, you can look back at the slides, and if you have questions, you can email us at PMD, you can email me, and we can walk through your particular design and the techniques that we have seen applied in lots of different customers, and then help you apply through that. So just transitioning quickly to new products that we have launched at PMD to try to solve this. So what this is showing is our older drive that was a cable connected drive. And it's a 1% of the weight, the newer drive. It's a kilowatt worth of power. This has been very popular in the robotic space, in mobile robotics and collaborative robots, where it's a solderable drive that you can put right at the motor, so minimizing the wires that you need to connect to the motor. And it supports all different types of networking interfaces. We'll also talk about distributed versus centralized architectures. So what it has is it's a pretty small 1.5 by 1.5 drive. It's a 3-card stack. It has a CPU that the user can download code into. It has our motion processor chip on one of the cards and a power amplifier, and it can drive up to a kilowatt of power. And what the onboard CPU helps you do is you can download user code to do all the intelligence that's associated with that particular axis. And you can connect to it via CAN, Ethernet, serial. So what you need when you have a cobot, you would have one of these drives per motor, and only wiring that's needed is your network connection, could be Ethernet or CAN, and power. So this kind of opens your options for newer control architectures. So what's inside, as we talked about, has a C-Motion engine, which is the processor that you can download code to. It supports newer encoders that are becoming more and more popular. So there's the serial BIS and SSI encoders, and you have the sine cosine analog encoder for very high precision motion. And it has, for safety, it also has 2 separate volt supplies, HV and HV-aux. So the HV for the high voltage, and the HV-aux stays on for low voltage, low power stuff. So you can still report faults and failures. So that's pretty popular in the cobot application. And this, where we talked about, you have few different ways of controlling it. You could have a hierarchical control architecture where the first drive is the master, and then you can connect the secondary axes to an expansion network on the drive. And that gives you an ability. So if you take a cobot with 6 axes, the external controller could talk to the first guy, and he's in turn controlling the remote axes. You could also do a flat network where all of them are on the same network. And you can host a lot of different CAN open and other protocols on the drive. So there's 2 different architectures. You can have the flat architecture or the hierarchical as shown here. The other nice part is the same drive controls all different motor types. So if you looked at the linear actuators that we talked about, those are brushless DC motors. So from our viewpoint, they look like a brushless DC motor. So you can control those, but you could also have some simple stepper axes, right? Like closing and opening a door or a valve or something. So the same drive can be used for controlling all different motor types. So What it is it's essentially a solderable drive. So you can make a small card which has your own custom connectors, and that way it gives you the customization you need, but you don't have to do your own design. So the card that you solder it to is very simple card, and it provides all the IOs that you need. And you can write C code and download it to the C Motion engine, and you can have the intelligence. So we have a few applications that are battery handheld kind of applications. So there's no controller. So all the code's running on the drive locally, and you can control the motor with that. So I'm an engineer, and I typically like to see an application example to see what these look like. So this is showing a cobot application where you see the drive, which is the N series drive, mounted on a board on a PCB, and it's mounted right at the motor, and you can see the size of it. So you can customize the connectors, make this card your own. And so it just has a motor connection, the power, and the network connection in this example. The other example we have is in the lab automation space where you have the Cartesian gantry. So this is a 3-axis XYZ controller. So where it's a centralized control, you have a simple 3-axis card, and you have your custom connectors wired up to each of these motors. So that kind of gives you a quick overview. I started off with force control and linear actuators just to educate you on what's used. Typically for the end effectors and the grippers, we then talked about a few control techniques to get the force sensing with and without torque and strain gauge sensors. And we talked about cascaded loops and filtering in between. Then we looked at a few other robotic challenges, right? We looked at the Cartesian versus non-Cartesian motion, the dynamic load management, translation lookup tables. And then we ended with kind of looking at our drive solution and a set of typical applications. I know this was a lot that we've covered, but you can always go back and look at the slides to kind of look at the flow of it. Back to you, Steve.
Awesome, Prab. Thank you so much for all of that there. Great presentation as always. So folks, we are in the Q&A portion of the talk right now. Again, there's plenty of time to get your questions in. I highly recommend you take advantage of Prab being here live right now with us to potentially answer any questions that you might have. And again, for those who are listening to this on demand, we're sorry we missed you live. Thanks for watching on demand. You can also ask questions that we will receive in our dashboard, and we'll make sure to pass those on to Prab as well. So again, please get your questions into that Q&A box that you hopefully see on your screen. First question here, sort of a broad question for you, Prab. Just talk about what are some of the programming capabilities of the PMD products.
Yeah, so in the mobile robotic space, what we see is actually these N-series drives that are mounted. So you can actually download code to them. So we have ProMotion, which is like a user window-based GUI where you can kind of buy a DK eval card and control it and set up stuff that way. So you can do it on the benchtop, and you can actually generate C code from it and download it. And you can write C. We provide a full C SDK, and so 90% of your code development is done with just a DK board before you have your own hardware that to develop. So it kind of helps you fork off and have software and hardware work in parallel, right? So it lets you kind of do that. And it's all standard C-based SDKs. And we have a lot of design examples that we could provide for different end markets. So that kind of helps people getting started and then starting to get programmed.
I'm curious, just what are you seeing, trying to stick with collaborative robotics if we can, just for a minute, one of the things that we're seeing in recent years is higher payload capabilities from these cobot arms, longer reaches, perhaps lighter weights, right, overall for these work cells. Just what sorts of challenges does that entail for you guys when trying to come up with your own innovations?
Yeah, I think even what we've seen is there's a constant push for being smaller because they want to pack a lot into that motor unit, right? The axis itself. So they want to be able to have enough space for all the wiring and everything else that has to go into it. So there's a lot of challenges in terms of size and in terms of the wiring. So we are starting to see more of, traditionally it's all been centralized control architecture. Like if you look at the big robots, right? Like the ABBs and the Kukas of the world, they were a big central controller and they were doing controls to PVT kind of points to the remote axes. So there was no intelligent at the axes. We're starting to see a lot of the cobots go towards, which mobile robots have already done, but the cobots also go to this intelligent axes. So where there's a little bit more of a distributed architecture with this lot of compute that's done at the axis, and so they can do more predictive maintenance stuff. And so as the payloads, as you were talking about, payload and reach gets higher, you want to try to do more predictive maintenance. So you want to kind of know when you've crossed a threshold. And since the driver, the controller is right at the motor, right? We can easily say, okay, this is what your typical range occurrence look like, let's say. And when you exceed it, or so you can have a lot of different thresholds set up. And we also have this capability of trace, which a lot of people use. So you can look at 7 to 8 different parameters over time. So say you deploy your cobot, you could say, okay, how did each of my axes do? What were these key 7 parameters? And you can download them offline and compare. And you can look at your mechanical construction. There may be one axis that's worse off than the others just because of the way the robot was constructed.
Oh, very cool. A question just came in here from Katate. Hopefully I'm pronouncing your name right. Just question is, what can you say about harmonic drives?
Yeah, so there are vendors that do. There are some like Harmonic does both motors and controller, and there are like us. We do the controller. That way, we are agnostic to the motor, right? So you can go with whatever different motor type you have. So those are two different architectural kind of decisions, right? When you're making, do you want to stay motor agnostic, or do you want to try to buy the controller from the motor vendor? Harmonic does very good motors, so we tend to work with them on the motor only side. They do have some integrated products in there.
I'm curious, when do you start working with a cobot arm provider, right? If they're, and how closely do you work with them? And I'm not looking for you to name any companies, again, sticking with, there was one of the leaders in this space recently, I think late last year, introduced their next gen cobot arms that could lift more, longer reach, that whole, trends that I was talking about before. But how closely do you work with them, and when do you actually have to start working with them if they're looking to incorporate one of your products into it, or build a new product for them into a next generation of their product?
Actually, we work with them like 4 or 5 years before new products get launched.
Yeah.
So typically, a lot of
Yeah.
them, what they'll do is they'll try to assess all different technologies that are available, right? They would buy a DK from us, just take a motor, even before they've done anything with cobots or the arm, and try to put it through the paces in terms of the controls and the current that they want to draw and all that stuff, and try to put a load. So you can actually simulate the load with the magnetometer. There's a lot of different setups that you can kind of simulate the load. So we tend to work with them very early on because it's more an architectural decision, right? And we tend to work with them in terms of reviewing the design to say, oh, centralized was it distributed, which one makes sense for this particular application, what did each of those look like? And we tend to actually also customize our control algorithms so we can update our chips with custom firmware where they may have a unique particular use case, right? Or they may want a specific sensor input brought in as a digital I/O or analog I/O, and they want to do something with it. So it's more an architectural decision. So we get involved pretty early on to try and understand what their requirements are. If they need custom firmware, and so they prototype. A lot of these guys prototype on the bench, and then there's 3 different arms, right? There's the electrical guys that prototype on the bench. That way they can give the software guys a platform to work on, and then there's the mechanical guys that are building, making sure they can actually deliver in that form factor.
Yeah.
So we tend to work out with them very early on.
You guys, so you know all the secrets about what's coming out down the road.
Yeah, but thing is, you don't know what's going to get commercialized. So there's a
Yeah,
lot
yeah,
of
yeah.
time that happens. So,
Yeah,
yeah, we work with a bunch of humanoid robot guys, which is very sophisticated. So there they have a super intelligent central controller that gets a lot of other sensor input. So the controllers are getting just the local current control and local feedback for controlling the motor, but there's like a central controller running a motion planner, doing all sorts of stuff with all different sensors that they have on board.
very cool. Another question here for you, Prab. What's the maximum number of axes that can be controlled by one of the standalone drives that you were discussing today?
Yeah, so the N series drive is a one-axis drive, so it controls one axis. We have cards that do four axes at a time. So we've been used in a few different 3D printing kind of applications where they have multiple axes. They would just buy the card with a four-axis controller. But you can actually essentially build an axis machine, like a cobot with six. So we have a synchronization mechanism, so where all the axes are synchronized for motion. So you can build a six-axis drive, a six-axis machine from it. And if you do that hierarchical kind of architecture, you can actually make it look like one drive. So the main controller is only talking to one drive, and the C code riding on one deconstructs it and says, oh, and by the way, this is a motion for this axis, and forwards it on to the other axis. So there's a lot of intelligence that can be built into the first drive that you talk to.
Another question, I think you talked about this a little bit, but recap, what are some of the benefits of distributed versus centralized motor control?
Yeah, in terms of centralized, it was the most common that was there before, right? The big robots had a lot of compute horsepower outside, and then they would wire in. But a lot of these mobile robotics kind of spaces where it's light and that even cobots are moving to this distributed control, where what you saw was the axis or the drive is right at the motor, and then all you're sending is power and in your network connection. Because the weight of the cables, actually, we did an analysis of the weight of the robot. The cabling actually adds a ton of weight. So from the robot point of view, to your point where they want to try to make it lighter, so the distributed architecture is getting more and more popular because the drives have become so sophisticated. You can actually send very high level commands saying, oh, I want to get to this point. And then the drives at each axis are kind of computing and they synchronize with each other. So distributed is getting more popular in smaller, like mobile robotics kind of applications, right? Where you have two drives controlling two axials and they talk to each other. The larger machines are still centralized because they want to kind of centralize the safety part of it. So they do all the profiling and stuff in the central controller and then send specific point commands to the individual axes.
What about, does that, so I know there's some cobots that can go back and forth between different modes, right? They can operate in industrial mode, high speed, when nobody's around. Does that impact the ability of a cobot arm to operate like that, what you're talking about?
Yeah, so that's actually all in the controls. So where we talked about the algorithms that are used, so they would have two separate modes. So they would have a force threshold mode. So you saw the force threshold when you stop moving. So you can actually force limit where there's no more motion at a certain force. So in a cobot, if it's collaborating with someone, as soon as it sees a certain amount of force, the motion stops. And there's another industrial mode, like you talk about, where they program it in the alternate motion mode, where the controller is allowing you to continue motion. So you've reached your gripper force, but you can continue your positioning, your motion on the robot. It doesn't halt the robot. So it comes down to how typically they'll program both modes and then they can pick and choose which mode it's operating in.
Yeah, very cool. Just want to let the attendees know, that we have updated the slide deck. That was our fault there. So the slides are available in there now. I think you just have to refresh your browser and then you should see the updated slides there. Another question just came in. Two more questions just came in. Is the control structure fixed? Or can I implement controllers other than PID like lead lag? Sorry.
Yeah, so there's a lot of sophistication in terms of the control algorithms that we provide. So we typically have current control with FOC, we have PID, but there's also other feed forward and other algorithms that you can implement, especially in these N series drives with the CPU on board. You can do an outer loop that can do lead lag stuff, and you can disable, you can still do PID, but you can set the parameters to allow the outer loop to take control. So there's a lot of flexibility there.
Cool. All right. Any final? I think we're just about out of time here. There's no more questions coming in. Again, if you're watching this on demand, we can't send these questions to Prab and the fine folks at Performance Motion Devices to answer for you folks afterwards. Just some closing comments from you, Prab, if folks are interested in learning more about how you can help them on their collaborative robotics journey. What do they need to know?
Yeah, so just reach out to us. If you go to pmd.com, pmdcorp.com, you can actually see there's a resources section with a whole bunch of white papers on all different type of applications. So if you go there, you can see all these resources, and if something interests you, you can reach out to us. We're always available. We typically work really closely. We are a motion control partner, so we tend to work with them, like this humanoid robot example I was giving you. They come to us with a concept. They say, oh, this is what we're trying to do. This is our architecture. This is how it's going to be structured mechanically. So we get involved that early. So we try to help them kind of figure out what the structure should be, because we are looking at it more on the controls point of view, right? Saying, oh, what else is missing? We have to add some firmware to get you the controls you need. And then they may have safety, lots of different. So we get involved early on, and you're more than welcome to reach out to us, and then we're happy to help you architect your next product.
I'm pretty jealous. That's what I would love to. I would love to have some insight into whether or not these robots are commercialized at some point. Just seeing what people are working on is fast. I'm going to come visit you sometime soon.
Yeah, you should.
Shadow you for a day and see all the projects that get sent your way. Prab, thanks so much as always for lending us your time today. If I don't talk to you, I'll see you in a couple months at the Robotics Summit, May 10th and 11th in Boston. Thanks again, Prab, for all your expertise.
Thanks a lot.
And of course, thank you. And thanks to everybody who attended today. This talk will be available on demand shortly. You can rewatch it by visiting roboweeks.com. If you're rewatching it, again, just use the same login information that you used today to access this talk on demand. One final thought, our next session in the Collaborative Robotics Training Series takes place April 5th at 2 p.m. Eastern. You'll hear from Universal Robots' Joe Campbell. He'll be running through a 10-point checklist on how to benchmark your cobot supplier. Again, if you're not registered for that one, just visit roboweeks.com to register for that and all of our upcoming sessions as part of Collaborative Robotics Training Days. My name is Steve Crow, Executive Editor of Robotics at WTWH Media. On behalf of everybody behind the scenes, thanks so much, folks, for tuning in. We'll talk to you again next week.